pharma, but not basically cognitive.
Okay, so you got your, you're getting your quizzes back that you took on Friday. For the most part, those went pretty well. By far, the most common mistake was to use 2 samp T-int on it instead of T-interval. We talked about the quiz right after you took it. No, we didn't. You guys turned it in and then left, right? So I will talk about it real quickly. Thank you. I would have forgot that. In the quiz, there was a before and an after and a difference, right, in a table. So first thing you have to do, you go through that series of questions. Is this a means problem or a proportions problem? It was water usage, right? Before and after watching a video, right? So that would be a means problem, a quantitative variable. So it's a means problem. Is it 1 sample or 2 samples?
2 samples.
2 samples. You got a before sample and an after sample. All right, so you got means problem, 2 samples. What's the next question you ask? Is it paired data or independent data? And this is paired data. Anytime you have 2 measurements on the same individual, in this case the individuals are families, there were 10 families, then you take the difference within each pair, which I did for you, and then you do T-interval on the difference. So this is paired data. So T-interval on the diffs. Now, quite a few of you, more than who didn't do that, most of you did exactly what you'd been taught in your notes. Put the before in L1, put the after in L2, then go to L3, tell it to do the differences. Well, I already did the differences for you. So what could you have done? Just enter the differences into L1 and you're done. You entered twice as much data as you had to if you did the other way, right? But the reason I went in and gave it to you so it wasn't so obvious that this was paired data. You have to be able to make that choice, right? You have to be able to do that. So T-interval on the differences. You then ignore the before and after values completely, and then when you do T-interval, you tell it you have data in whatever list you put your differences in, and you should have gotten an interval. Somebody who got the quiz correct, tell me what it was. It was like negative 3.22?
228, yeah.
228 to positive 6.228, like that?
281. 228. Yeah, you're
okay. All right, so then the next thing it said on the question was, and provide the correct interpretation. So what's the correct interpretation of this?
We're 99% confident the mean difference lies between the two.
Good. We are 99% confident that the mean difference is in this interval. Some of you lost the point because you said, I'm 99% confident that the mean water usage is in this interval. Right? Well, just the fact that it has negative values in there, you can't have negative water usage. And so it's the word difference has got to be in there. Okay? And then the last part, or part B, said, does this interval provide sufficient evidence that the video works? And the answer is no, because?
It contains 0.
Because it includes 0, which means no difference. 0 difference is plausible. It's possible that there's no difference at all. Right? There were a few people that make a really common misinterpretation and started talking about individuals, saying, well, looking at the befores and the afters, some of them went down, some of them went up. So yeah, there's some evidence that it helped. When I say use the confidence interval, I'm talking about the mean. Is the mean different than 0? And the answer is no, 0's in there. Right? So confidence intervals don't tell you anything about individuals. They only tell you about means or proportions, about population parameters, not about individuals. Another common misstatement about a confidence interval, and not so much when it's differences, but people will say, this confidence interval I'm 99, or this confidence interval means that 99% of individuals will be in that interval. It doesn't say anything about individuals. It's 99% confident the mean of all individuals is in that interval. Got it? Okay, well I told you when you took the quiz that I would grade it pretty easy. You'd get 5 points for your name, so that was the starting point. So if you got more than 5, you go, okay, that's a victory.
Did anybody get 0?
Nobody got 0. Well, yeah, some people who weren't here got 0. You had to be here to get those 5 points. Okay, so today we get to start hypothesis testing. And hypothesis testing is really just another way of making inference from sample data about the population. We've already been doing that with confidence intervals. And in fact, there's nothing that you can do with hypothesis testing that you can't already do with confidence intervals. The two give the same results. And I actually prefer confidence intervals. I don't like the hypothesis testing thing, but that's pervasive in scientific research these days. Everybody wants a hypothesis test and a p-value, so you have to understand it. Right? So I'm going to make you understand it. I'm going to make you know how to do it. But just remember, you can always check yourself with a confidence interval. Confidence intervals people get better than hypothesis testing. So the idea of hypothesis testing, it really goes back to the old scientific method that you learned in, what, 6th grade or somewhere around there? What's the scientific method?
Hypothesis tested.
Okay, you form a hypothesis based on observations.
Tested.
Okay, but how do you test it?
Experiment.
You do an experiment to collect some data.
Analyze the data.
Then you analyze the data and see if it supports your hypothesis. If it doesn't, you reject that hypothesis
And substitute
you reform the hypothesis and you start all over, right? Well, in statistics, we get to stop at that step where we either support the hypothesis or we reject the hypothesis. We get to stop there. But if we're part of a research team, then they would be the ones that would cycle back. We do another experiment and try to form it. But in statistics, the hypotheses that we want to test need to be mathematical expressions about population parameters, right? So the book, I won't pull that down and show it, but the slides that the book has make statements like, you've all seen this. 4 out of 5 dentists recommend Crest toothpaste or whatever, right? Where does 4 out of 5 come from? And is that claim real? Or is it true? How would you test a claim like that? So, to write that claim, 4 out of 5 dentists recommend, is that a mean or a proportion? 4 out of 5. That's a proportion. 4/5 is 0.8. So they claim that P is 0.8. Well, to test that claim, we could go do a survey of dentists and say, hey, what kind of toothpaste do you recommend? Right? And we could actually test this claim. So that's how we do it in statistics. We'll collect data based on random sampling from the population. We'll compute a sample statistic that's used to estimate the population parameter the claim is made about. And then we'll see how well our sample data, our sample statistic, matches up with the population claim. That's hypothesis testing. So to illustrate this whole thing, well, first of all, I got to give you a couple of definitions, right? So capital H with a sub-zero is the notation for what we call a null hypothesis. And the word null in the English language means what?
None.
None.
Null and void.
Right? So, yeah, when they say null and void, the null hypothesis means there's nothing going on. There's no change. There's no difference. Like the water usage thing. The null excuse me. The null hypothesis would be that there is no difference in water usage, right? So none. The alternative is generally the claim that we want to support. So claim that researchers hope to prove. That's not always the case, but in general, that's the way the alternative works. And it's a mathematical opposite of the null. So in probability lingo, these are complementary events. The null is what must be true if the alternative is not true. Okay? So let's practice a little bit about null and alternative hypotheses. Here's some of the homework problems that you're going to have to do. Will be kind of like this. Determine the null and alternative hypotheses for the following scenario. At so-and-so community college, the syllabi for online classes state that students should expect to spend 10 hours per week doing coursework for each 3-credit hour class. You've heard this before, right?
Yeah.
I think my online students would say, oh, it's way more than 10. The director of e-learning is concerned that the students are being required to spend more than 10 hours per week. Determine the null and alternative hypotheses for this scenario.
Null would be 10 hours, alternative would be anything above 10.
Okay? Is that right? He said the null would be, okay, now, let's see, I kind of covered it up, so let me do it here. The null hypothesis and the alternative hypothesis, we need to make mathematical expressions with the symbols that we use for population parameters. So hypotheses always have population parameters in it. So first thing, is this a means problem or a proportions problem? I've heard both answers. Luckily I haven't heard anything different. You said means. Why do you say means?
They're looking at the main hour number of students have to spend per week.
I don't think it ever actually says the word mean, but it's number of hours per week. That's a quantitative variable. So this is a means problem. If it were a proportions problem, it would say something like the percent of people who did, or something like that, right? Or 4 out of 5 dentists. So this is a means problem. So what's my symbol I use for population mean? Mu. So mu will be in both the null and the alternative. Now we write out the claim that they want us to test. So it's the director of e-learning that's making the claim. So what does the director of e-learning believe about about mu?
Greater than,
That they spend more than 10. How do I write that as a mathematical expression? Greater than 10. Okay, so I got that down. That's cool. What is the null hypothesis? I said that it is the mathematical opposite of this. It's the complement. So what must be true if this is not true?
equal or less than.
Equal or less than. So mu is less than or equal to 10. All right? So you're done with that homework problem. Wow. So there's their answer. Do this one. This one's a little harder. After learning that so-so from Switzerland can hold his breath for 19 minutes and 21 seconds, man, that's serious. A group of students decided to conduct their own science fair project around the amount of time an average adult can hold his or her breath. Part of the group found research to suggest that adults can hold their breath for 30 seconds when submerged in lukewarm water. I got to hit page down because it's too long for one screen. The other half of the group found evidence to suggest that the mean time is different if water temperature is colder. Right? So that the average time you can hold your breath is different if you change the water temperature. The water temperature is colder. The group would like to test this claim. Okay, what's this claim? The mean time is different if the water is colder. That's the claim they want to test. So write down the null and alternative hypothesis. You write it on your paper, and then I'll come around and look at it. I can't get the others. I can't get both slides on here at once, but so you have to remember the other one. Excellent. I can read this has to be low. Okay? I haven't said that yet, but that's going to turn out to be the case. Think about what the word null means. Right? The average for adults is 30 seconds. But now they want to test something about cold water. Null would mean there's no difference in cold water. Right? None. No change. No difference. No nothing. Okay? If I can use you as an example. She's doing exactly, she's not done, but she's doing exactly the way I want you to do it. Okay, I'm not sure of the symbols yet, but I know it's going to be mews, because this is a means problem. So she's got her mews down there like I have. And then she's got 30 in both places, because that's what we're testing about 30 seconds. So this is how far she's got. So now that all that's left are symbols. My little camera. I'm too fast. There we go. So this claim, it says, is different. Is different. What is that symbol mathematically? Not equal. So that's not equal. Now how do I know that goes on the alternative and not on the null? Because null means no difference. There would be no change because of the cold water. So it should still be 30. Right? So that's the answer to that problem. So one thing to get from this is the null will always have an equal sign. The null always has equality. It'll either be a straight equal sign like it is here, or it'll be a greater than or equal, or a less than or equal. Okay? So null always has equality. The alternative, oh, I can't spell today. Alternative never has equality. So it will always be either a not equal symbol, a less than symbol, or a greater than symbol. The null will always have an equal symbol, a less than or equal, or a greater than or equal. So this one always has equal, this one never has equal. Got it? Okay, so I want us to look at one more here. A leading news authority claims that the president's job approval rating has dropped over the past 3 months. Previous polls put the president's approval rating at a minimum of 56%. This is old data. But the president's chief of staff is concerned about this news report since it's an election year, and he wants to run a test on the claim. You write it down, null and alternative. Okay. That symbol's wrong. Yeah, no, that one. Me. Think about it for a second. You getting answers yet? Wrong symbol. That's horribly wrong symbol. And you're doing the same thing. What is the population parameter here that we need to test about? Let me ask the question in a different way. Is this a means problem or a proportions problem? Proportions problem. So what's the symbol we use? P. It's not mu this time, it's P. Right? So this is a proportions problem. So P and P. Then the claim that we want to test claims the president's job approval rating has dropped. How do I write that? It's less than
Equal to 6%.
less than 0.56, right? P less than 0.56, that's the claim. Now we decide, is that the null or that the alternative?
That's an alternative.
That's the alternative. How do I know it's the alternative?
No equal.
There's no equal. So what is the null hypothesis?
Greater than or equal.
Greater than or equal to 0.56. Now, I didn't see anybody doing it, but a common thing would be to write the number 56 instead of 0.56, but that's just kind of semantics. You've got P, by definition, is proportion, not percent. But they've said everything in terms of percent. I probably wouldn't get picky about that on a test. If you put P less than 56, I'm just going to say fine, particularly if you put the percent sign. Right? But in the online homework, they may get picky about that. Although these will probably be done as multiple choice. They'll give different combinations of nulls and alternatives, and so you're not going to have to type it in yourself anyway, but just in case. Okay, so now I'm going to do a little illustration of this. Let me shut this off for a second. I brought with me a brand new deck of cards. I actually got to go to China this summer, and I brought home this deck of cards. Tell me what that says.
No idea.
Well, I can't even tell if it's upside down or not. I don't think there's an English word on this box anywhere. But we're gonna take this down to the basics of cards. You don't have to know a whole lot about playing cards, but we do know that in a deck of cards, what proportion of the cards are red and what proportion are black? 50-50, right? Proportion. Now, there's 52 cards, 26 of them should be red and 26 of them are black. So if I write that down using mathematical expressions, the proportion of red cards should be 0.5. Right? So what we're going to do is,
Yeah, what about jokers?
well, hopefully they put the jokers at the top or the bottom and I can pull them out. But if we hit a joker, we'll just toss it. How about that? Hopefully the Chinese know how to play cards. Yep, there's the jokers right on the bottom. So we'll take those.
There is
Well,
English.
they're
There is
really
English
black.
on the box. Plastic. It's on the red.
On this?
No, where your pinky is.
Oh, it's a website. Go there and see. No. Okay, so rather than spend the time to shuffle the cards, because technically, you may not know this, but statisticians will tell you that to get a deck truly random, you need to shuffle it how many times? 7, that's right. How did you know that? Someone told me. It's a lot of people, it's around 6 or 7, but 7 is the number they usually give. So when you go to the casino, make sure they shuffle. So rather than shuffle, I'm just going to fan through the deck, and you can pick anywhere you want. That's the same as shuffle, so it makes it random, right? So pick a card, and then we're going to keep track of whether those cards are red or not. And so that this is binomial, we're going to replace it after we look. So what'd you get? So you got a red card. So put it back anywhere you want in the deck. Okay? Anywhere I want in the deck. You pick a card. It's also red. So stick it back in there. Right? So we got 2 cards. Keep track of total number and red number. Okay? Got red too. Anywhere you
They're all red.
Let's check it. Red.
red again.
Oh my god.
Come on, guys. Who can draw a black card? You can draw a black card, right?
It's gonna be this man.
No.
No way.
Red card.
No. Freaking.
Okay, now you're seeing that even though something is unlikely, it can theoretically happen. Oh, no.
Oh.
Red card. Jacob? Get us a black one.
I'm pretty.
It's red.
It's
How many is that?
This is rigged.
7. Pick the top one. You don't want the top. It's red. That's the second time that card.
No way.
Alexis, there you go. Give me one. How many is that? 8? I need 2 more.
No way. No.
Another red one. Why are you smiling at me like that, eh?
This is crazy.
And red. Gosh, is that 10 cards?
Yeah.
What is the chance of that to get 10 out of 10?
It's rigged.
Come on, boy.
Wow.
So what you're saying is based on the data, you're not sure this claim is true?
Pretty sure.
Well, that would be the null hypothesis, wouldn't it? Right? The null hypothesis would be that there's no difference between this deck and a normal deck. So this would be my null. What would the alternative be? Not equal. Now, we go collect some data. Scientific method. We draw 10 cards randomly from the deck, and then we see if the data supports the null hypothesis. Right?
Is there actually a black card in there?
So our data said X was 10 out of 10, so P hat is, what's P hat? 1, right? 1.0, 100%. Right? Now, I know you guys are thinking I'm cheating. So, inspect this deck. Okay, I did cheat. They're all red.
How can we trust you?
How can, it's a brand new deck.
Too weird.
Yeah.
But there was a black joke.
Chinese decks are different.
Red.
No, they're not different. I bought 2 decks.
Oh, there's an all black.
I bought 2 decks,
How do you know?
and I very carefully unwrapped them, pulled them out, resorted so that all the black ones are in this deck and all the red ones are in this deck. Then I wrapped them back up and put a little piece of cellophane on. But the reason for doing this Yes, I'm a cheater. But the reason for doing this is seeing what it's like to do hypothesis testing in practice. We have a claim that often people completely believe, but they've never collected any data on it. So how much data is enough to convince you to reject this null hypothesis and support the claim of the alternative? Now, it's funny to watch psychologically what happens as you go through the process like this. First one, oh, it's red, okay, fine. Second one, red, oh, I got 2 in a row. Yeah, that's fine, no big deal. 3, no big deal. 4, people are starting to kind of frown at me a little bit. And then, when were you absolutely convinced that you rigged this deck?
Somewhere over there.
I wasn't.
Around me.
Around you. And you were 8th one? 7th?
Fifth. I was 6.
I still wasn't convinced. I like to believe in the magic of the world.
People start to get really suspicious after you get 5 in a row. And by 8 in a row, there's nobody, probably, among you, that was not convinced this can't be right. So what we do when we do hypothesis testing is we set what's known as a rejection region. How many red cards in a row will it take before I reject the null? And you set that in advance, right? And it's based on probability. So what is the probability that you could get X of 8 or more given P is 0.5? So this conditional probability, the given part is my null hypothesis. So in a hypothesis test, when we compute probabilities and we decide if we have sufficient evidence, it's all based on assuming that the null is true. So hypothesis test, assume the null is true, and then see how weird your data is. Is the data what you would expect if the null were true, or does the data lead you to believe that null must not be true, which is what happened here. This leads us to believe that null is not true. So what is the probability you could get 8 or more? And that's the point where everybody was absolutely convinced, and you started saying, let me see that deck, and they're all red, and, you know. What's that probability?
Oh my God, it's magic.
Now we made this binomial, right? So when I ask you that question, what is this probability? You should, oh, I know how to do that. Because I've mentioned, right, that the final is comprehensive. We've had binomial probability. What is this probability? Well, it's a greater than or equal, so it's 1 minus binom CDF of N was 10 cards. P, if the null was true, P was 0.5. And since I do 1 minus, I have to turn this around. This goes down by 1 to a 7. Right? So it's the complement of getting 7 or less is getting 8 or more. So what is this probability?
.0547.
0.547. Okay? That is a very low probability. If there's a 5% chance that you could get 8 or more, that means there's a 95% chance you couldn't get that if the null was true. If I set this as my cutoff for when I'm going to decide he's cheating, if we get 8 or more, then he's cheating, right? Then this is known as the significance level. Which we'll denote as alpha, Greek letter alpha. And do you remember the relationship between alpha and confidence level? We've had alpha before. Remember? We used alpha to figure out what the t critical value was. Right? And we said 1 minus the confidence level C is alpha. So if I have an alpha of 0.05, what's my confidence level? 95%. Right? So this is going to be used as a cutoff or rejection region for deciding that no, your data does not support that null. Now the actual probability you get from your data, the data wasn't 8, the data was 10. That's going to be an even smaller probability. So when the probability associated with the data gets less than this cutoff, the significance level, then we reject the null. Right? So alpha is the cutoff, that's a good word to say, the cutoff for how small the probability of getting the observed data before we reject the null. So alpha, the significance level, is the cutoff that we use for how small the probability is when we compute the probability of getting the observed data, given the null is true. And if that probability turns out to be really small, then we're going to reject the null. Well, how small? Well, below alpha. And almost always alpha is set at 0.05 or 0.01 to go along with 95% confidence and 99% confidence. What's the probability of getting all 10?
0.
No, I don't think so. What's the probability that x is 10 given p is 0.5? Is it possible you could get all 10 red cards if it was a fair deck?
Sure.
Sure, it's possible. But how likely? That's what I want to know. How likely?
9.767 put to the negative 4. E to the
So
negative
9 point what?
Well, it's 9.76
Times
6, put it e to the negative 4.
Okay? So as a decimal, or moving the decimal, that's 0.123976. Right? So yeah, it is possible to get all 10 red cards from a fair deck, but it's very unlikely. That's roughly 1 in 1,000 chance of that. So this is called a p-value. P for probability. So let me come over here and I'll write the definition for p-value. The book does not give the definition of a p-value yet in this section. They wait a couple of sections, but I just can't get through this talk without talking about the probability. So I give it. P-value is the probability of getting sample data, or I'll say a sample statistic. Getting a sample statistic as far or further from the null hypothesized, this is getting to be a long sentence, hypothesized parameter, population parameter, as was observed if, and it's a big if the null is true. That is a mouthful. P-value is the probability of getting a sample statistic as far or further from the null hypothesized population parameter as was observed if the null is true. In other words, we got a sample statistic, p hat, of 1. The null hypothesis was 0.5. That's a long ways away. right? So what's the probability you could get that far away from the null hypothesized value of 0.5 if 0.5 is really true? Well, that's this value. Probability of getting 10 when p is 0.5 is very, very small. So then we take the p-value, we compare it to our significance level, 0.05, and say, well, it's even less likely than this 95% confidence would tell us, so we're going to reject the null. So if the p-value is less than alpha, reject the null. Okay, so now let's go back to the data from the quiz. And I guess none of you have the data from the quiz. So I can pull it up here, but I want to do the confidence interval that we did on the quiz, but also show the basics of a hypothesis test based on that. Okay, so there's the data, right? So we talked about it at the beginning of the class, so you know now that I need those differences put in a list. So if you don't already have them in a list, get them in a list real quick, but I need to hurry a little bit. So the difference mean was 1.5, right? I just remember that. I don't remember the standard deviation, so I need you to help me with that. But put these differences into a list, doesn't matter which list, and then do t interval on that list.
Confidence level.
Let's do 99% confidence. What'd you say?
Standard deviation is 4.6.
Okay, standard deviation of the differences, that should be a D, is 4 point what?
6.
6, and that's several zeros, right? So
There's 2 of them, yeah.
yeah, so that's good enough. Okay? Now, let's write down the null and alternative hypothesis. Instead of a confidence interval, what if I said do a hypothesis test? What would the null hypothesis be? First of all, is it a means problem or a proportions problem? It's a means problem. So I need a mu. What would the null be?
Equals 0.
Equals 0. Very good. How'd you get 0?
Because that would be no change from before.
Because that would be no change from before to after. So what's the alternative?
U does not equal.
Mu does not equal 0. Okay. Now you could say, since this wasn't set up that way, if they had said test the claim that the water usage is less after the video, then you would have a less than symbol, right? Depending on which direction you did your subtraction. So you'd use either a less than or a greater than symbol, not a not equal. But we're just going to test that it's different. Did it change? Okay. So do t interval and give me the confidence interval.
Negative 3.228
-3.228
to 6.228.
6228. Okay. And we did that earlier, right? Now, look at this interval. Does this interval allow me to reject the null hypothesis? Is the null hypothesis in there? Yeah. So if it's in there, it's plausible. You can't reject it. Now, can I say this data supports the null hypothesis as being true? Or usually people would say it as, I accept the null as true. Does it tell me the null is true? No. It says what?
The The null is possible.
The null's possible. The null might be true. But it might be -3 too. It might be -1. It might be 5. Right? It might be 0. So you never can say, I accept the null. You have to say it as, I fail to reject the null. And that's going to drive you nuts for a while. Why do I have to talk like that? That's not me. Fail to reject the null. Or there is not sufficient evidence to, right? So you have to fail to reject. Right? So the way a hypothesis test works is you compute something known as a test statistic. And a test statistic is the number of standard errors that your sample data is away from the null hypothesis. The sample data is 1.5 minus the null hypothesis, which is 0, divide by the standard error. The standard error, remember, of a mean is standard deviation over the square root of the sample size, which was 10. Somebody do that for me real quick. Take 1.5 and divide by this ratio. .03. Okay? This number is the number of standard errors that our sample mean is away from the hypothesized mean. One standard error away, that's not very far. So we're going to get a p-value that's not significant. So we say, well, this could happen by random chance. So here's my distribution for d bar. If the null is true, that would be centered at 0. But we got 1.5, and that's just about exactly one standard error away. The p-value is the probability of being that far or further, and it's a not equal symbol, so it's in either direction, so you get a big p-value. Not less than alpha. You would fail to reject the null hypothesis. Okay, well, I ran out of time before I got to do another example from the homework, but they'll give you a scenario and say, what's their conclusion? Do they reject or do they fail to reject? Right? So, work on that. Send me emails if you have questions.